Hello and welcome to Building Skills in Data Collection and Understanding Variation. I'm Bob Lloyd and I'll be your guide today as we explore these discussion topics. We're going to start with thinking about what I call the three phases of performance measurement. We're going to talk about the components of the quality measurement journey and then dive a little more deeply into two specific aspects of data collection and also beginning our journey in understanding variation. We're going to couch all this in terms of the model for improvement, the IHI standard way of thinking about all improvement strategies. And today our focus is going to be really on thinking about the three questions and how particularly the second question, how will you know that a change is an improvement, actually fits into our overall strategy. We've talked before about building our aim, that is understanding what we're trying to accomplish, the first question. And the third question about building changes is that part of the team's work that comes by building some strategies that's going to allow them to move forward. But today, our plan is to really look at this second question. How will we know that a change is actually an improvement? That is, when we've made the changes, how will we know? Well, it requires, first of all, having a baseline, understanding where we are on the particular measure or measures that are relevant to our project, and then being able to get that data compared to the data after we've started to make some changes and ask, did the process get better, stay the same, or get worse? As we go on this journey, though, I think it's incumbent to start by asking a question that relates to aim. That is, what is the actual aim of your measurement work? Too many people think that all measurement is the same. There's a wonderful article that helps us understand this. It was written by some colleagues at an organization called ICSI, the Institute for Clinical Systems Improvement in Minneapolis. Leif Solberg, Gordon Mosser, and Sharon McDonald wrote this wonderful article that was in the Joint Commission Journal a couple years ago that really sets the tone for this. We're increasingly realizing not only how critical measurement is the quality improvement we seek, that's the second question, but how counterproductive it can be to mix measurement for accountability, public judgment, accountability, with data for research and data for improvement, what they call the three phases of performance measurement. So let's explore this a little bit. In the article, they provide a very good diagram that helps us think about various aspects of what we're doing in our data measurement work. They then compare improvement, accountability, and research as the primary categories, if you will, for organizing all measurement and data work. They then identify a number of methods that cut across each of these and then fill in the cells. Now let's start talking about some of these by thinking about research. As an academic, this is where I was trained for many years, in the research principles. Now, in doing research, our goal is to really build new knowledge, to test theories. Great example of this happened recently when one of the space shuttles came back. In the vacuum of space, they had built and created the purest crystals that human beings had ever seen. And they brought these back. They were all excited because it really challenged existing theory. They built new knowledge. They tested theories and then debunked certain theories about crystalline formation because they'd never been made in the vacuum of space. So they're being interviewed back on Earth, and the interviewer asks one of these scientists, so what could we do with these crystals here on Earth? And the scientist says, absolutely nothing. There has no utility for this because right now we can't replicate the vacuum of space in its purity here on Earth. And so the reporter kept saying, what could we do with this? They were asking questions that related to improvement, and the scientists were talking about issues related to research. That is, we could build new knowledge, we could test theories, we could write journal articles that will evaluate the existing theories in light of what we've learned. You see, when we do a lot of research, we don't do PDSA, Plan, Do, Study, Act. We oftentimes do PDSP, Plan, Do, Study, Publish, Plan, Do, Study, Publish. There's a different set of criteria involved with this. We set up tests that are blinded or controlled, either through experimental or quasi-experimental designs. We design them so that we eliminate bias. That is, we control for extraneous variables that could confound our results. We get what is called just-in-case data. That is, you go and get data, and then you get a little more just in case somebody comes up with another question. So you end up usually with very large data sets. We have fixed hypotheses that relate to something that we call the null hypothesis, that you either accept or reject based on usually one large test of comparing time 1 with time 2, and then you use statistical test of significance, namely p-values. You get a chi-square, a t-test, you get a p-value at the 0.01, 0.05 level, and you ask, is this data set, time 1, different than this? And when it is, you can determine that it is significant at the 0.01 or 0.05 level. Now, all of this is about research. It's a very different set of criteria that drive our work over here than when we come over here or over to here. Now, let's think about accountability. Accountability is driven by the need to know, are you doing better than you did last time? It's a very simple question. State data commissions do this a lot, where they compare by quarter or by year, and they'll get data on hospitals or providers and say, time 1 compared to time 2. Are you better, worse, or the same? If the number's the same, they conclude that you haven't changed. If it drops and lower is worse, then in fact they conclude that you've gotten worse. And if you go up, obviously you've gotten better. Now what's interesting in this kind of comparison, I'm always reflecting on one of the things that Dr. Deming said. He made this great, he always came up with these points that they seem so profound, but so simple. He said when you have two data points, there's a very high likelihood that one will be different than the other. It's just that simple. So variation exists in the fact that you have two data points. It's going to be very likely that one does differ. So if you're into the judgment or accountability mode, you're going to have really no test. You're just going to compare things and ask, are they different? You're going to measure and try to adjust for bias sometimes. Sometimes a state data commission might use a severity risk adjusting methodology to account for severity. So people don't say, my patients are sicker than yours. So they'll adjust. They'll obtain 100% of whatever data is available. There'll be no real hypothesis to test. It's just a question of, are you different? Yes or no, by a little bit, by a lot. There are really no tests. There's no change focus. Now, this in contrast to what we do in improvement, again, differs significantly. We're trying to improve care, either the efficiency or effectiveness of care. We're going to do a very observable test. We make our tests transparent and we allow everyone to see them, and we post the results so people can understand what we do. We accept a consistent bias, and we're going to try to set up our data collection plans to introduce factors that will control for extreme amounts of bias. We're going to get just enough data rather than just in case data. We're going to get just enough. That is, we don't want to overburden the workers, the frontline staff, the nurses, the physicians. They've got more important things to do, taking care of patients, and their life is not spent collecting data. So we're going to get just enough data that is based on sequential sampling that allows us to have rather flexible hypotheses that might change as we learn and gain knowledge. We're going to do sequential tests over time, and we're going to use statistical process control methods, namely run and control charts, to understand the variation that lives in the data. Now, the important thing, as you think about these three phases of performance measurement, is that one is not necessarily better than the other. They all have great utility. We rely extensively on research to provide us the foundation for understanding the efficacy of drugs, treatments, and procedures. It's a very fundamental part of actually doing improvement. Accountability occurs not only in the external world when groups, organizations, regulatory bodies, for example, want to know, are you better than you used to be? But internally it happens when the board says, how are we doing? They don't care about all the micro-level things. They want to know, how are we doing, as do the senior management team frequently. So accountability has its place, as does research and improvement. The problem is, if you're not clear about what's driving your measurement aim, in fact, you'll send mixed messages to your people. You'll send mixed messages in terms of the methodology, and eventually you'll start to look at data in a very different fashion that can be confusing. Bob Brook and his colleagues at the RAND Corporation have written a very good article that helps highlight this in a little different way. Brook and his colleagues wrote this article, and they distinguish between efficacy as being the foundation for research. That is, we do double-blinded randomized trials to understand, is this an efficacious treatment, procedure, or diagnosis approach given the etiology of the disease and what we know about it. And we set up these double-blinded trials to test drugs or procedures. They also go on to point out, however, that efficacy takes a different path than what we do in quality improvement, and that is about efficiency and effectiveness. A mother who brings her febrile infant into the ER takes no comfort in being told, oh, don't worry, do you know that the wait time last quarter was statistically different than the wait time the same quarter a year ago? The mother wants to know why I'm not getting treated right now. A physician waiting for his or her stat troponin to come back from the lab takes no comfort in being told that there's a significant p-value between the wait time for this test this month compared to last month. You see, quality is all about efficiency and effectiveness of stuff happening right now. Now, the other issue related to this goes beyond the concepts. It goes to how we look at data. On the bottom here, we see what many would call data for judgment. We're going to look at these data, and when they fall out beyond these modified box and whisker plots, we're going to say bad data, not good. Or, depending on the direction, up or down. That's not important right now. The issue is they fell out of some anticipated range. Notice, however, what happens when we look at the data on a statistical process control chart, a Shewhart chart. In this case, we're looking at C-sections, so this is the percent of C-sections. And notice that these three data points are now nuzzled between the upper and lower control limits, which is a signal that they reflect just random common cause variation. Notice also that there's a data point over here that was nuzzled between these confidence bounds, but in fact it exceeded the upper control limit. So in this case they actually missed what we would call a special cause that popped up when we put it on a control chart. Now, what is the difference between these two approaches and these two graphics? Well, these data down here are totally independent time periods. That is, each bar is totally independent of what went before it or what comes after. Now, the illusion is that somehow this represents a process because the data are plotted by month. In the top graph, what we have done is looked at the variation in all the dots. We have the center line, which is the average, and then we compute the upper and lower control limits. This is showing data as a process, and we look at the variation in the whole set of data, whereas on the bottom, what we're looking at is a single data point by itself with no connection to what went before it or what comes after it. Data for judgment leave us only to conclusions. Is it up? Is it down? Is it good? Is it bad? When we look at data for improvement, however, it puts us into a very different mode of gathering knowledge. Here's another good example. Notice that these four data points exceed the upper confidence boundary on these little bars. When you put them on a control chart, notice that they are very easily nuzzled right in the middle of just random common cause variation. If you looked at the data this way, you would have a tendency to overreact and say, ooh, bad data, good data, depending on the direction. Whereas up the top, we would say this is just common cause variation, and we would take a different approach to understanding what we need to do about it. So as you think about your own journey, it's really important for you to understand what is driving the aim for your measurement. Is it research? Is it accountability? Or is it improvement? All three have their place, but all three will take you in different paths as you think about the quality measurement journey. For us today, what we're looking at is to think about the steps that we need to go through in order to build good data sets so that we can start to understand the variation. As we lay this out in a sequence, we're going to start with a concept that comes from our aim, in this case, freedom from harm. The concept that we might look at is reducing falls. You could reduce meds, you could reduce infections, errors, etc. But in this case, we're going to look at reducing falls. From that concept, we build a measure. In this case, a falls rate. We have an operational definition of what would be the numerator and the denominator. And then we develop a data collection plan. We go get the data, and then we start our analysis to turn it into action to run our PDSAs. So today what we're going to do is really focus on these three components. We're going to focus on data collection, developing some strategies, and then once you have data, how do you start putting it into a framework for improvement? You've picked some measures, you've cast your net out into the sea, and now you're going to gather some data. One of the first questions that one needs to understand, though, is how did you get those data, and are they representative of the process as it varies over time? Two strategies work very nicely in thinking about data collection. One, understanding stratification, and two, building skills in sampling. Let's talk first about stratification. it is not so much an issue related to statistics, it's related to logic. That is, somebody needs to ask, as you go to collect data, does this differ by time of day of week, shift, type of patient, age of patient, whether they have comorbidities or not? All of these things can confound the data. So when we talk about trying to build data sets to reduce bias, you want to try to get the data to be as homogeneous as possible. Stratification is a very simple thing, but it requires somebody up front asking the questions, raising their hand and saying, does it differ by these various characteristics that might influence the way our process works? Here's an example. If you don't have an understanding of stratification, you might get data that look like this, where you have extremes in the data. Now what happens here is if you compute the mean, x bar, the average is a mathematical artifact that you have extremes in the data, one set that's up here and one set that's down here. The mean doesn't reflect actually anything. There are no data points at the mean, but because you've got a bimodal distribution, you get two extremes, the average is right in the middle. If this was turnaround time, and these are turnaround times for day shift and turnaround times for night shift, you should really make two separate charts. Crack it apart and look at them separately, because the overall average isn't reflective of the process. Here's another example. This was actually a hospital's data that I looked at. And then it went, then it went, and then it went, then it went, Now, what do you think this might be? Most people very quickly realize that this is day of the week. And what they were looking at was not only revenue, but also admissions and other volume activities. So it was Monday, Tuesday, Wednesday, Thursday, Friday, Saturday, Sunday, and so on and so forth. Again, the mean would be skewed toward the high end, even though it wouldn't really reflect the true mean of what it is on the weekday or the true mean on the weekend. So stratification is the first thing that we'd like people to think about in terms of being able to put their data into relatively homogeneous buckets. The second piece is about sampling. Many healthcare people, while they get great education, have not been trained adequately in sampling, in my opinion. I've asked people, have you ever pulled a random sample? And they say, oh, sure. Hey, how did you pick it? Well, we pulled open the drawer and we randomly pulled out a chart. That is not pulling a random sample. The first question is, what would a random sample or any kind of sample look like if it was drawn properly? Well, it would reflect the shape, size, centering, and the distribution of the total population if you went back and matched your sample against the total population. What happens is many times people pick data that end up being a biased sample. You end up having a negatively biased sample or a positively biased sample. And what happens here is if you pull data that are negatively biased, you actually end up having a much worse opinion of yourself than you really should. If you pull data that are positively biased, you end up feeling a lot better about yourself than you really are. A properly pulled sample should actually replicate the size, spread, and centering of what the whole of the population would be like. Now, we go about doing that by using some techniques. These techniques have a very rich history. Sampling as a discipline actually goes back only a few years. One of the classic stories was when Franklin Delano Roosevelt in 1936 was running for yet another office as president. He was running against a gentleman by the name of Alf Landon, smiling Alf right here. And the Literary Digest, which was a magazine somewhat like the Reader's Digest, polled over 2 million voters and predicted with great deal of confidence that 15% victory would go to Alf Landon over Roosevelt. Now, if you remember the conditions at that time, coming out of the Depression, Roosevelt had quite a following. And yet they predicted that Landon would win by 15% and were very clear on it. Well, what happened? The Literary Digest people used telephone directories and automobile registrations to pull their sample. Now, think back, who had cars and telephones in 1936, the rich or the poor? The rich. Well, who were the rich? Republicans or Democrats? They were Republicans. So what they did was go out and poll the people who were going to vote for smiling Alf anyway. And what happened is they forgot how popular Roosevelt was. With Republicans, with Democrats, pulled people out of the Depression, helped bring the country back on its feet again. And so Roosevelt won by a large landslide, and actually the Literary Digest went out of business. They lost such credibility. Well, it also happened that there was a young guy by the name of George Gallup who was running around at that time, and he started doing some of this sampling stuff as well. What he pulled was a stratified quota sample and was able to accurately predict that, in fact, Roosevelt would win. In 1948, Gallup and his company suffered a severe blow, however, when they predicted that Truman would actually be beaten by Dewey. And this headline is just a classic headline that appeared in all the papers of the country. Dewey defeats Truman. And what happened in that case is that Gallup forgot the concept of exit polling. So when they were sampling, they finished their exit polling too soon. This was a much closer election, and people didn't make up their minds until they were actually in the booths voting. And then they never got these people as they came out and asked them. And so Gallup took a severe blow to their credibility, but were able to recover, and today Gallup, Harris are two of the leading polling companies in the country and have led the way on developing sampling strategies in many quarters. There are basically two bodies of sampling, probability sampling and non-probability sampling. Having basic knowledge of these skills will take you very, very far down the road in getting data that are valid, reliable, and representative. Now, a lot of people think you need many, many pieces of data in order to get a, quote, valid or representative sample. Think of this. When the ABC Nightly News poll takes their sample to ask, do you favor the president's policy on this or that or any topic? Out of 300+ million people, those polling agencies poll only around 1,000 people. But what they do is develop very sophisticated sampling methods that combine a variety of the probability sampling tools. Not just a random sample, but they'll do a stratified random quota cluster sample, where they'll cluster parts of the country in regions, and then within that they'll stratify and do other types of sampling. So they can pull a highly, highly effective sample with only about 1,000 people representing 300+ million. But it's all based on statistical probability. So as you build knowledge of sampling, it's incumbent to understand some simple things. Probability. Random probability sampling means that everybody in the population has an equal chance of being pulled. And you do that either through a random number generator, which many statistical packages have, or you can use a random number table found in the back of any good stat book. I don't care how old the stat book is, it works. And you use a method to go through that table, pull some random numbers. Now, if you want to get a little more fancy, what you do is develop a proportional stratified random sample. So now we're going to take the population and we're going to look at strata. In this case, medical, surgical, OB, and peds. So we're going to stratify first, and we're going to ask what percent do each of these strata represent of the total population. So say that medical is 30% of our business. Well, when we go to pull our sample over here, 30% of that sample should be medical. If surgery is 40% of our business, then in fact 40% of the sample should represent surgical patients, and so on. Now we've replicated how something occurs in the population in that same sample. It requires a little more knowledge of the population and a little more data so you can start getting enough in each bucket that you've stratified in to make them properly representative of the total. Now, what Deming offered is to move beyond these sampling strategies. These are what we would call enumerative, because oftentimes you go out and get a sample, you may only get one sample. You may not even get two samples. What Deming offered was to move to what he called analytic approach to sampling. That is to be able to combine small doses of data, but get many of them over time. Instead of getting a whole bolus of data, a huge database, and then go analyze it, get small doses over time. The way I think of this is thinking of water and a stream. Let's say that the EPA was interested in looking at the water quality in a river or stream. They wouldn't go to that stream or river and take a 10,000-gallon bucket of water and then leave. They would set up a sampling plan, and if they thought that somebody was polluting upstream, they would say 9 o'clock, 1 ounce, 9:15, 1 ounce, because the probability of the liquid having the same ingredients in 1 ounce as it does in a 10,000-gallon bucket is probably the same. I mean, think of this. When we draw blood from a patient, we draw a small vial. We don't take a pint, a quart, because the assumption is that the blood coursing through our system, just like the water coursing through a stream, has a representative mix of ingredients in it. So you can take a sample. What Deming indicated to people is that if you pull repeated samples in small doses, you're going to understand how a process lays itself out over time. The two top sampling strategies are typically you go out and get a sample and stop. When ABC does an evening news poll, they go out and get a sample. They don't keep sampling. They go out and get one large sample and then analyze it. We're going to do that differently. We're going to get small samples repeatedly over time. This is in many ways the same thing that happens when we hook people up to telemetry. We get multiple readings on the output of that patient's processes over time, and they're tracked on telemetry. And we can look at them over time. So as we think about sampling, it's incumbent on us to gain knowledge of not only the techniques and the methods, but the pros and cons of using one over the other, and being able to get, particularly for quality improvement, data that allows us to build knowledge over time. Deming added this notion of judgment sampling to this discussion by saying that what you need to do is talk to the people who have knowledge about the process and then use that knowledge to pull your sample. So if I'm working in a clinic and they tell me that it is absolutely crazy here between 8 and 10 in the morning, with that knowledge, I'm going to pull a different sample between 8 and 10 than I might the rest of the day. I'm going to use that knowledge to make some judgments about how to partition and collect my data so that it properly represents the process over time. So two things that we want to think seriously about: data stratification and sampling, both of which will help you build much better skills in data collection. Now, poof, you've gone out and obtained data through some method. What do you do with it? Deming had a very simple method. He said that just reduce variation. You know this yourself. Waiting for an airplane to take off, waiting for a restaurant. You go into a restaurant and they say, oops, we don't take reservations here. Here's a pager. Go have a seat. We'll page you when there's a table ready. Some people would just get up and walk out. It's too much variation. I want a reservation that I can come and sit down at that designated time. Variation exists in all that we do. And what Deming's basic charge is to think about the variation and then reduce it, because reducing variation will make things more pleasurable for the customers. The problem is that in healthcare, we have a long-standing history and tradition of using aggregated data and summary statistics to try to make sense of the variation that lives in our processes. Here's an example. Look at this road sign. Is this road, in fact, safer now than it was in time period 1? We've gone from 90 deaths to 61. Judgment would say, ooh, good, fewer deaths. Then you find out that, in fact, the road was closed for 6 months because a bridge was out. Now, if you wanted to make a big deal over it, say you're the mayor running for re-election, you could say, folks, this is a marvelous result. I have reduced the deaths on this road, therefore you should elect me. I'm a mayor that's safety conscious. And then somebody does point out that the bridge was out and the road was closed for half the year. It's very easy to jump to conclusions when you have two data points. Maybe in the future, given the transparency push that's in healthcare today, maybe we'll see signs like this. Deaths, number of MRSAs, number of central line infections, number of readmits, and they'll be posted. Hospitals would take issue with this because the data don't have a context. Here's another way that we do this in healthcare. Thank you for coming to the Quality Council today. I know that many of you cannot see these numbers in the back of the room, and probably some of you in the front can't see them either. But you know, we have looked at these numbers. They are very good. We've analyzed them, and we think we're doing quite well. Thank you very much. Now, another approach is to make little bar graphs or pie charts and look at data. Again, thank you for coming to our Quality Council meeting. I have great news today. We have gone from 70 minutes of cycle time down to 35. Look at that. That is a monumental decrease. Look at the size of this bar compared to this little bar. Then somebody says, but, well, we had several units involved with this. How did they do? You go, okay, well, let's look at these. Here is where we made the intervention, right here. Here's the average of 70. Here's the average of 35. Here's the average of 70. Here's an average of 35 afterwards. And finally, in Unit 3, here's the average of 70 at time 1 and the average of 35 at time 2. Now, which of these units is actually making substantial and significant improvement? It's interesting that many people pick Unit 2, and what happens is they've been lulled into seeing what they think is, quote, a downward trend that just kept going. Now, if this unit actually did have significant improvement, you would have seen after they made the change not just a continuation, but a major inflection with a drop that was due to the fact that you did something. This is just reflective of an ongoing pattern that started way back here when it started going down. So this is really not from an improvement strategy, the unit that improved. This one, most people would say it got better at first, but then what happened? It continued to get worse after that initial period. This could be a result of the Hawthorne effect, where people change their behaviors and then slip back to their old ways, but this unit definitely didn't improve. Finally, we look at Unit 1. We see that the data started up here at the baseline. After the change, they shifted and moved to a whole new level of performance. Unit 1 is the only one that actually reflects the overall aggregated statistics. Unit 2 and 3 do not fit into the summary aggregated statistics. And yet, if you use this approach with the bar graphs, you would think that everybody achieved the same results in the same way. Here's yet another example. Boy, do I have good news for you folks. We had a CABG protocol, coronary artery bypass graph, and we made that protocol change right here. And I am here to tell you, this stuff is so good. We have gone from 5% mortality down to 4%. And look at the size of this block compared to this block. You don't even have to know anything about statistics, and you can see right away that we have had a significant decline. Just look at the size of those blocks. Then somebody might say, well, I think the size is related to the fact that you haven't calibrated the y-axis to be a very big, and you go picky, picky, picky. You're getting too wrapped up in the details. Look at the size of this block compared to that block. It is a significant drop, marked by a 20% decrease in mortality. This is billboard kind of stuff. Put an ad in the paper. We are going to shout this from the top of the hospital. Then somebody says, well, how did we do by month? Channel 5 Action Cam is parked outside, and they got our data from the State Data Commission, and they're comparing us to other hospitals, and they think that we are not as good as what we claim. So let's look at the data by month. There was a period when you had 8% mortality. Not good. Then there was a period where we had a run of about 6 months when it was down around 2%. Ooh, good data. So forget that. Let's talk about the 2%. Oop. Where are we currently? Well, currently we'd have to say that, well, we're about 7%. And then somebody would come up with a brilliant idea. Don't show them data this way. Show it to them this way. Because they can't understand the true variation. This is aggregated data. If we plot the data over time, you see that mortality, even though the average was 5% at time 1, 4% at time 2, the average is not reflective of what's happening to the process. Mortality was actually going down before we made the change. After we made the change, mortality actually started increasing. And if you were to bring a member of your family to this hospital now to have a CABG, would you have great confidence that they were able to keep mortality low? Well, not really. Current performance is about 7% mortality, but they tell you that the average. So as we compare aggregated summary data with data over time, we start to see a very different view of the world in light of what our improvement strategies might be. You see, if you don't understand how the data lay themselves out over time, it's going to be very hard to understand performance. You can have the same mean, center line. Let's say that our mean is 45 units of something. Doesn't really matter for this purpose. You could get that average by data that look like this, by data that look like this, by data that look like this, or data that looked like this. Finally, you could have data that actually were just a random process like this, and they all produced exactly the same mean. Now, depending on the measure that you're looking at, the data going down might be good, or the data going up might be good. It all depends on the directionality of the measure. your operational definition, and how you're trying to capture that aspect of the process. But if you don't understand the underlying variation in the data, you really have no chance of improving quality over the long haul. So we're going to try to start looking at data in a different way. And when you do that, you oftentimes gain a new view of reality. Now, as you look at this graph, how many black dots do you see? Just stare at it for a moment. I had one guy in class one time say, there's entirely too many dots. Now, what's interesting is this is not an automated graph. This is a flat, static graph, and your eyes are doing this because of the combination of the black and the white and the gray. The other thing that's really interesting is the looks on some of your faces look exactly like the looks I've seen on management team when they are given data that don't fit their view of reality. You're sitting there going, oh, look at that. Then you talk to the person next to you, go, do you see that? I don't see that. That's exactly what happens when people in meetings start looking at data that somehow don't fit their view of reality. And when you do that, there's usually a couple things that happen. If you don't like the data and it doesn't fit your view of reality, you either distort the data, distort the process that produced it, or you kill the messenger. The best way to go about it is to try to gain knowledge to make sense out of the data, because sometimes reality starts to fool you. How many legs are on this elephant? Again, probably too many. But as we think about our data, sometimes you're going to find insights that don't mesh the way you view the world. Data should give you knowledge. They should help you build strategies for dealing with the conditions of the process and where you want it to move over time. So the key to understanding variation is not to use aggregated summary statistics, but to look at data over time and to plot them. Now, there's two basic approaches. Most people in healthcare have been trained and given some background in what we call static views, enumerative statistics, where you learn something about the mean, the median, the mode, measures of central tendency, and what we call measures of dispersion or spread. Anytime you collect data, there is value in using some summary statistics to understand how that data was collected and how it compares to what we call the normal distribution, that humpy bell-shaped curve that people always refer to, as if they knew it well. Every time you collect data, you're going to get a distribution of some sort. Sometimes they're going to be peaked, sometimes they'll be flat, sometimes they'll be skewed to the right or to the left. The key is understanding these three aspects of any kind of data. And it comes by looking at static enumerative statistics. The centering, the mean, median, or mode, the spread, the min, the max, the range, the standard deviation, or then the shape. In this case, it has two modes. It's what we call a bimodal distribution. Other times we get data that have only one hump, but it might not be centered. It might be skewed. So there's value in looking at data, but it comes in looking at two pieces, where the data are centered and how much spread. Look at these two distributions. They have exactly the same mean, 45. Are these two distributions the same? Right away you say no. And you say no because you understand something about spread. But if all I showed you or told you was the mean, you would have a very different view. You'd say, well, the average wait time to see the doctor is 45 minutes. Both processes are the same. I don't know which one I'd pick. But now if I show you how much spread, the min to the max, the range, the standard deviation, you gain new knowledge. So anytime you're using descriptive statistics, if somebody just gives you the mean, you legitimately should ask them, what do you mean? Because if they don't give you some sense of spread, you'll only gain part of the picture. Now we're going to take these concepts, however, and we're going to move away from static data and think about dynamic data. Think about how we plot data over time and are able to look at things as they lay themselves out, not in a static distribution, because data are fixed. In a static distribution, our classic kind of bell-shaped curve, there is no time reference. Time has been removed. And what Shewhart, Deming, and Juran helped to teach people for decades was that if you take data and you lay it out, imagine that there was a little string right in this distribution that you could pull. And if you pulled all the data out and laid it out over time, you would see a process. And as I showed earlier, that average could be produced by many combinations of dots, data that went this way, data that went this way, and all those other combinations. And what Shewhart tried to get people to understand is that when you do this, you have the ability to understand two aspects of variation: common cause and special cause. And therein lies the heart of understanding variation from a quality improvement perspective. Common cause, it's data that reflects variation that is just random. It's part of the inherent design of the process. It's due to what we would call regular or natural causes, and it affects all the outcomes of a process. It results in what we call a stable or predictable process, and the variation is essentially random. Think about your drive to work. You ask people, how long does it take you to get to work? And they say, oh, about 40 minutes. Well, that about 40 minutes suggests that there is some upper boundary or lower boundary. It could take me as little as 30, but as much as 60. And that's what I'm used to in my variation. That's random, up and down. But the day that it snows, or there's a major accident, or there's a train wreck blocking the road, in fact, now you're into what we would call a special cause. Due to irregular or unnatural events, it affects some, that is, people on this road where the accident was. Everybody else is moving along okay. It results in producing what we call an unstable process, and it is what is known as assignable variation. Think of this from a patient perspective. We talk about a patient looking at their temperature, regular normothermia, and then all of a sudden, boom, they spike a temperature. A spiked temperature is a reflection of what? A special cause. And there are many, many examples in physiological aspects of medicine. Elevated blood pressure, INR ratios, milligrams per deciliter blood glucose. All types of measures have reference ranges, and then when we see them exceed, people talk about, ooh, that's out of range. Now, they may not always say it's a special cause, but it's that same concept. I think there's a lot of similarity in what Shewhart, Deming, and Juran were trying to teach people for decades in healthcare and in medicine particularly. Much of the medical model is based on understanding common random variation and understanding when things get knocked out of whack. So a patient's blood pressure, normothermia, all these things have common cause, and then they can move into special causes. So our job is to be able to understand the data well enough that we're able to distinguish common from special, because you take different strategies depending on the type of variation you have. Now, to help us think this through in a very practical way, look at my pumpkins here. When you look at these pumpkins, would you say that they are more or less alike, common cause or special cause? Most people look at these and say, well, they're basically the same, a little variation, common cause. Now, if I showed you this bad boy, people right away say, ooh, that's special cause. You see? Common cause, special cause. But if I showed you a panorama picture and showed that there were carts in this parking lot and they all had large pumpkins or squashes, and this was actually a competition at a fair for large pumpkins and squashes, now they become common cause, and these folks are what? Special cause. Common is not good, special is not bad. Oftentimes people get that as a wrong conclusion. They think that common cause good, ooh, special cause bad. You may have a special cause in turnaround time or admitting time that was here, and then for a week it ran down here. Well, it's a special cause, one you'd actually like to emulate because the process was actually functioning better. This is the heart and soul of thinking about this. One is not good, one is not bad. They merely describe variation. Your job is to understand it so that you can make sense of it. If you look at this example that I have about blood pressure, that the average systolic around 165 and ranged 160 to 170. On systolic, this is stable, it's very predictable, little variation, but is it, what we would ask in the next question, acceptable? And you would say no. Therein lies the opportunity for improvement. Common cause, stable, predictable, but if it's performing at a level that is unacceptable, then there's your opportunity for improvement. If the process has spikes and valleys and special causes, in fact, that offers a different opportunity. You've got to address those special causes, figure out why they're in the system, and extricate them before they keep repeating and coming back and messing the process up further and further. This question of acceptability is key to understanding common and special causes. If the process is stable, common cause, the question is it acceptable? There's actually two questions when we teach this that we want people to think about. Is the process stable, and is it capable? That is it stable, common cause, and then if it is it capable of meeting the expectations of the customer? A process can be stable but not capable. And those are two key aspects of thinking about data and particularly building skills with run and control charts. Is the process stable? Is it capable? And those are the two challenges that we face. I think there's a lot of parallels in medicine. On the top left, we see common cause variation shown on a control chart, a Shewhart chart. On the lower left, we see normal sinus rhythm. And if you're skilled at reading EKGs at the heart station, you would look at this and say, patient's doing okay. Now, you may not say, ooh, common cause variation, but the concept really is the same. It's stable, it's predictable, it's just random variation, and it shows us the patterns that we expect in a normal rhythm. On the top, we see a control chart with special causes, data that have exceeded an upper control limit. There's been a shift. You'll see a whole lot of data parked above the center line. Well, at the EKG station, a cardiologist looking at this particular readout would say that is not normal common cause. This is something that's called atrial flutter, and it's designated by things called P waves that start popping up. And you can see right away the difference in the patterns. Common cause, special cause. There's so many similarities in the medical profession that we have for thinking about this. I think Drs. Deming, Shewhart, Juran would be very pleased to think of how easy it should be for those of us in healthcare to make the translation to what they were thinking about in understanding variation over time. Now, there's two main tools that we're not going to go into today, but you need to build knowledge about run charts and control charts. They are the two primary tools for understanding variation. A run chart is a plot of data over time. Time is always shown on the horizontal axis. We put the dots in chronological order. And if you ever really are stuck in thinking about what to do with data, it's just very simple. Here's the charge. Just plot the dots. It's just that simple. Just plot the dots, chronological order, connect them with a line, and when we make the run chart, we're going to put the median, which is x with a tilde above it. And then we're going to use 4 simple run rules to understand whether there are non-random patterns in these data. That, again, is the whole crux of what we're trying to establish here. Random versus non-random. And on the run chart, there's 4 simple rules that we use. On the control chart, we have a little different picture. We still have data over time. We have the measure on the y-axis. Now we're going to have the mean, x bar, as our center line rather than the median. And we are going to introduce 2 new concepts called the upper control limit and the lower control limit. These basically are parameters that show the variation in the process. You don't set these. Depending on how much swing and variation there is in the data, they will be determined and calculated by the chart itself. The more variation, the wider the control limits. The less variation, the tighter. Now, one realization is that there's basically one way to make a run chart. There are many ways to make Shewhart control charts, which is a class in itself. Today, I just wanted to introduce the 2 main tools, the run chart, one we start with when we're just beginning our work in quality. It's a little less complicated, but you can also miss some special causes that you will never miss on a control chart. So as we think about our data, we've come full circle today. We started thinking about why are you measuring, thinking about the differences between research, improvement, and accountability. We then moved to think about 2 specific aspects of data collection, namely stratification and sampling. In sampling, we talked about probability and non-probability. Finally, we talked about building an understanding of variation. That is, a conceptual understanding of variation, mainly played out through the use of our knowledge of common and special causes. And then finally, building up to understand how we would depict that variation on graphics, namely a run and control chart. I hope you found this session to be useful in building some initial skills. I would encourage you to take advantage of the references shown at the end of the presentation to build your knowledge. Hopefully, this session today will allow you to think about what you know, what you don't know, and build a learning plan so that you build better skills in the realm of data and understanding variation. Thanks so much for your time. Take care.